Hi everyone, this is the video on section 4.7. In this section we're going to talk about what's called the row space, column space, and the null space of a given matrix. So let's start with the definitions. So let A be an n by n matrix. First, the row space of A is a vector subspace of Rn spanned by the row vectors of A. So if you have an n by n matrix, you have m rows, each of which is going to be a vector in Rn, right? Because each row has n components. So if you're going to use those m row vectors to span a space, that is going to be a subspace of Rn. Similarly, the column space of A is a vector subspace of Rm spanned by the column vectors of A. So now here is a subspace of Rm that is spanned by those n column vectors. Now finally, the null space of A, this is actually nothing new for us because null space of A is basically the set of all solutions for the homogeneous system given by Ax equal to 0. Now this is the space that we were referring to as the solution space when we were talking about section 4.5. So what exactly do we need to understand about these spaces? So let's just talk about that. What we need to understand is, first off, do elementary row operations affect these spaces? So here what we're talking about is, suppose that you have original matrix A, and as you know, you can apply that elementary row operations to produce, say, an REF or something like that. So the question here is, the original matrix A and any REF of the matrix A, do they have exactly the same row space? Or do they have exactly the same null space? Or what about the column space, right? That's the question that we're trying to answer here. And even if they are not the same, can we get any kind of useful information from an REF of a matrix about those spaces? And how do we identify linearly independent row or column vectors of a matrix? Now, you can imagine that this is going to be a pretty important information if you want to find a basis for each of those spaces. And of course, the final question is going to be, okay, so it's nice to be able to identify linearly independent vectors, but how can we find actually a basis? And once you find a basis, by counting how many vectors are in a basis, can we actually find the dimension of those spaces? So in the next slide, we are going to answer the question addressed in the first bullet item, and in the slide following that we're gonna tackle the last 3 bullet items. So what do those elementary row operations do to those spaces, row space, column space, and the null space? So here is basically the punchline. First off, now if you think about the fact that elementary row operations, we have 3 of them. One is you can scale any row, and you can interchange any row. Now you can imagine that interchanging rows really isn't gonna change the row space at all. But also the third one is going to be scalar multiply one row and add to another. Now that's like forming a linear combination, so that really should not change the row space either, because everything in the row space should be linear combination of row vectors anyway. So here we go. Elementary row operations do not affect the row space or the null space. Now, the last part about this, elementary row operations not affecting the null space, we already knew that because we knew that elementary row operations going to preserve the solutions to any systems of equations anyway. So that's actually nice, right? So this means that I can start with the matrix A, and I can basically look at the REF of the matrix, and those two things have exactly the same row space and also the null space. Now, unfortunate thing about that is, here's the second part. Elementary row operations do change the column space. So the matrix A and the REF of a matrix A, they do not share exactly the same column space. It turns out, however, though, an REF of a matrix actually tells us quite a bit about both the row space and the column space of a matrix. So let's talk about that next. Now remember that given the matrix, when you form an REF by applying the elementary row operations, there were things called the leading ones, and also those columns that contain those leading ones, we call those the pivot column. And I don't know if you remember this language or not, but those positions of leading ones are called the pivot positions. So we're going to be using that terminology in this discussion, but there are actually three things that I would like you to know. The first thing is that the row vectors of an REF that contain the leading ones, those form a basis for the row space of a matrix A. So this actually follows the fact that the original matrix A and REF of a matrix A, they share exactly the same row space. So we can definitely use the row vectors from REF of a matrix A to actually come up with the basis for that. The second thing is the pivot columns of an REF form a linearly independent column vectors. Now, I cannot actually say that these pivot column vectors are going to form a basis for the column space because, as we discussed in the last slide, original matrix A and a REF of a matrix A, they do not share exactly the same column space. However, though, the third point is this. Even though those two column spaces, right, one for the original matrix A and one for an REF of a matrix A, they do not have the same column space. However, what we can say is that if you can identify the pivot columns for an REF, we can take exactly the same position in the original matrix, then those vectors actually form the linearly independent set of vectors that span the column space of the original matrix. So here's the third point. The columns of a matrix of the matrix A from the same pivot position that you identify for the REF, that's going to form the basis for the column space of A. So let me just try to clarify this. So suppose that when you look at an REF of a matrix A and you identify that the column 1 and column 3, for example, happen to be the column with the leading ones in it. So those are the pivot columns. So for the REF, if that is the case, then the original matrix A, you can also take exactly the same column 1 and column 3. Those two are going to form linearly independent set. In fact, those two are going to form a basis for the column space of A. So let's finish this video with an example. So consider this 3x4 matrix A. And so really the question here is, can we find a basis and the dimension for the three spaces that we talked about for any particular matrix A? So the row space, column space, and the null space. So let's just briefly talk about the process here. If you are going to find a basis and the dimension for the row space, what you need to be able to do is to basically just find an REF of a matrix A and then look at which row contains the leading ones. And those row vectors that has the leading one basically becomes a basis vector. So that's actually pretty simple to do. For the column space, for that, what you need to be able to do is to look at the REF and identify which columns contain the leading ones. And what you want to do is not just using those column vectors from the REF, but identify which columns that is. So if it's going to be column 1 and 4, then what you need to do is to then go back to the matrix A and pick out those column 1 and column 4, or whichever ones that happen to be the pivot columns, and then you use those column vectors from the original matrix to form a basis. Now the null space of A, I want to remind you that this is exactly the same thing that we were doing back in section 4.5. So look at some of those homework problems that were assigned. I believe those are like the first several problems in 4.5. And in fact, we did an example in class to find a basis for a solution space. So it's going to be the same procedure for that. So let me just say that about these. And what I'm going to do is to write up a complete solutions for that. So after you try these 3 questions on your own, you can compare your answers to what I'm going to post on Canvas as the written up solutions for that. So this is pretty much it for section 4.7. There's just one more little tiny things that I do want to talk about, but I think I'm gonna wait till Monday after I come back from San Diego to talk about that. So thank you for watching.